So hello everyone. Deconstructing inheritance, the name of my talk. You can find the slides up on the link seen on the screen. Let's get started. So this is my grandmother. She sadly died 3 years ago, and my mother and my uncle inherited her. When we say that, we don't actually mean that my mother is my grandmother, and we definitely not mean that my uncle is my grandmother or they are somehow a grandmother. Also, we don't mean that the goods that were used to be my grandma's are not both at owned by my grandma and to my mother and my uncle. They just passed on, just like value semantics. We move them from my grandma to my mother and my uncle. That's what we do in real life. In software, when we have an inheritance, we say derived is a base, and derived inherits the behavior of the base, but both base and derived would share the same behavior at the same time, right? Unlike in the real world in which the goods just pass from my grandma to my mother. This talk is about deconstruction, and here is the definition that Merriam-Webster puts up for deconstruction, and we are going to focus on the second part, the analytical examination of something such as theory, often in order to reveal its inadequacy. That's what we are trying to do in this talk here, and we do that because inheritance is somehow important in C++. I'm not sure exactly what's the reason behind it. People often think about C++ as a mainly object-oriented programming language, which is not necessarily true. And whenever they say that, they often think of inheritance as the main feature that they should be using in C++. Therefore, a lot of the code base that we have in C++ heavily uses inheritance. The talk will focus more on the inheritance, not necessarily on polymorphism that is typically associated with inheritance. So let's quickly go over this. Why is that we use inheritance in C++? We use it to model real-world concepts. We use it to reuse members. We use it for subtyping, and this is typically associated with polymorphism. And we use it to implement an interface or multiple interfaces or whatever. Those are kind of the four main use cases for which we are using inheritance in C++. This is the agenda of the talk. Has 6 sections. I'll go over them. Some of them are longer, some of them are very short. So let's go with the first one, simplest problem are hard. And this is a very old problem, you probably hear it by now. Let's design 2 classes, a rectangle class and a square class. And we have to have some basic operations on them, get and set the dimensions and get the area. That's it, just very simple problem. If we use inheritance, we basically have 2 solutions for this. Either square derives from rectangle or rectangle derives from square. Those are the two main solutions with inheritance. Let's pick up the first one. Rectangle is a square. This is the code that you would typically see. And rectangle, of course, derives from square, and it overrides, in this case, get area and add some more functionality. Doesn't necessarily look right because of several things. So first, it's mathematically incorrect. We cannot say that a rectangle is a square. The second thing, which it is apparent when you look at the code, is that the rectangle class is polluted by the square members. So it doesn't quite make sense for rectangle to have get size and set size. Of course, you can hide them, but still you do have them in your public interface, one way or another, directly or indirectly. And then The other thing, the Liskov substitution principle, which is always associated with inheritance, the test for inheritance, it's broken. Let's look at one example for this. So let's say we have a function that increases the area, and it receives the base class, a square, and it sets the size to be twice the size of one edge. And by doing that, we expect the area to be 4 times bigger than it was before. But if we pass a rectangle here, that's not going to be the case. So this function will not properly work whenever we substitute a rectangle for a square. Let's look at the other way. Square is a rectangle. This is how the code will look like. A little bit less typing, but still not right. It does fix some things. Mathematically, this seems correct. Indeed, a square is a special type of rectangle. The interface is less polluted. You can hide the things that you don't need, but it still doesn't work. You have twice as much storage that you need to actually represent a square. You only need 1 dimension, and you have 2. And LSP, the Liskov substitution principle test, that's broken. You cannot apply Liskov substitution test for this. And same type of test that we are applying here. You have a rectangle, which is your base class. You set the width to be double the width you had before, and because you're changing only the width and not the height, you expect the area to be double. But if somehow you pass in a square, you're going to change both things at the same time, and this will fail. So if you inherit a square from rectangle, you may break your client code. The first fix that you can do here is to make your classes immutable. That is, once you construct the object, you cannot change it anymore. And this is how it would look like. I'm still having inheritance here. And that basically gets rid of the setters, so somehow it fixes one of the biggest problems that we have in there, but still is not quite okay. You still have twice as much storage you need in square, and inheritance really doesn't buy us anything because you can't do anything with that. The proper fix is actually to remove inheritance. You have 2 independent classes. Yes, they may be mathematically related, but in your code, but they have nothing in common. And let's look at what Bob Martin says about this. The truth is that square and rectangles, even immutable squares and rectangles, ought not to be associated by inheritance. So this coming from Bob Martin, who's working in OOP a lot, that means a lot. Going on, he makes the following remark. The class square is not a square. It's a program that represents a square. The class rectangle is not a rectangle. It's a program that represents a rectangle. The fact that the square is a rectangle does not mean that the representative share the either relationship, right? So mathematically, we do have that relation between square and rectangle, but if we transpose that into programs, we don't need to have that relationship anymore. And this is another code that I find very, very insightful. Is useful when trying to model real-world relations to make class hierarchies intuitive. But classes are metaphors, and metaphors, if extended too far, will break. So in our code, when we say rectangle, that's just a metaphor for the real thing that we are trying to model. The actual mathematical rectangle is not the real mathematical rectangle. So in this section, we talked about 2 of the things for why would we use inheritance. And in both cases, we ended up with a conclusion that we should not use inheritance for those types of things. Let's move on. The grand is-a confusion. So what is this is-a thing that we keep associating with inheritance? Let's try to model a simple system, an elevator system, and just look at the buttons. An elevator typically has a lot of buttons inside of the card, outside of the card, floor buttons, stop buttons, alert buttons. And there are multiple ways in which you can do that. Again, I'm focusing on inheritance. You can have a base class, a button, then you can have a travel button, and you have some buttons that are on each floor, and you have some buttons that are inside of the card, and then you have rescue button, and you have stop button. So this this type of here, he tries to put the emphasis on the type of commands that that those buttons will execute. There's another way you can model this. You can still have a button base class, but you can say, I'm dividing this into two big categories, inside button and floor button. The inside button is the rescue button, stop button, and go to floor button. And then the floor button is just an up button and a down button. And yeah, depending on the type of elevator, you may have different things. Or you can model this in a third way, and just no inheritance at all, but just have a concrete class that has some inner details on how the button will appear and what the function will do. And here the emphasis on the behavior of this button. Let's look at those alternatives with inheritance. Which one is the real world? If you look at the elevator that you use most frequently, which one do you think represents the real world? Well, to me, none of them. I don't think of an elevator as having inside and outside buttons, and I don't have that image in the real world. There is no such thing. And part of that comes from the confusion, what is a button? You can think of a button of an elevator. There are multiple types of buttons. You can have arcade game buttons, you have mechanical keyboard UI buttons, which are completely different from the other types of buttons. You have old bell buttons, we don't have electrical parts. What's the essential thing of a button? You can't properly capture that in real life. Some buttons are electrical, some are not. Some of them stay pressed after you press them, some are not. Some of them you can physically press them. Some of them, like UI buttons, you can't just push with a finger. They are all buttons in real world. We do have a problem. We can't simply relate the concepts that we have in software with the real world buttons that we have out there. In real world, things like button are concepts, which are somehow the building blocks of thoughts. They're just fuzzy generalization. I have some idea of what a button means. Somehow I can press it, not necessarily with my finger, not necessarily electrical, but somehow I press that thing. And we typically do that by similitude. We can't find one example of the actual button concept in the real world. We just have instances of the buttons in real world. There is no such thing as the button. If you do see one, please let me know if you do find the button in real world. In software, on the other hand, we do have these concepts as a set of instances, and we can say we have a button in software, and they are just representative for a class of objects that we have there. We do have sharp distinction what's a button and what's not a button. We typically do that by regular means of software construction. And they are generally algebraically constructed. So you have this, that, and the other that goes into a button, and nothing more or nothing less, depending on how you look at it. The is-a relationship in real world is not quite as we use it in software. So in real world, you can't think of inside button, which is a button. You can't find this is in real world. You can find it in metaphysics, but not in actual physics. In software, you can find this is-a relationship, which is typically associated with inheritance, but you find it in two different contexts. So you find it whenever you talk about reuse data layout and methods, and you talk about it when you're referring to substitutability, and that is basically the core essence of Liskov's substitution principle. You can pass a derived object instead of a base object. In the first one, that reuse of data layout methods, you can also do it with composition and a little bit more typing. And substitutability thing is just the essence of this Liskov substitution principle. We'll talk about the first part later, but let's now focus on the second one. And I'll start by having a quote from Sutter and Alexandrescu. The easy description of a public inheritance is misunderstood when people use it to draw irrelevant real-world analogies. A square is a rectangle mathematically, but a square is not a rectangle behaviorally. Consequently, instead of is a, we prefer to say works like a, or if you prefer usable as a, to make the description less prone to misunderstanding. That's from the chapter Public Inheritance is Substitutability, inherit not to reuse, but to be reused. So basically, they argued that we should completely abandon the notion of is a, and instead try to use the notion works like a. We have to think of public inheritance as substitutability, not is a. Rectangle is not a square, or derived class is not the base class. It can be used to be substituted into context in which you can use the base class. We don't have such a thing in the real world. You can't model real world with that. And what we are used to say with is just a metaphor. It doesn't make sense. It's just a big confusion that we have in software, just to trying to put all these concepts together into one single place. Okay. So in this chapter, we focus on the model of real-world concept, and we basically shown that it doesn't quite hold up. So we can't properly model real-world concept with inheritance. It doesn't work that way, at least not in an intuitive and direct way. So let's turn our attention to Liskov substitution principle. We've been mentioning it so far a couple of times. Let's dive deep into that. I think that's the core of inheritance. And if we figure out how this Liskov substitution principle applies, then we can draw a lot of conclusions about inheritance. So first, let's go over what Liskov substitution principle is all about. So I'm quoting from the '94 paper. Subtype requirement: let phi of x be a property provable about object x of type T, then phi of y should be true for objects y of type S, where S is a subtype of T. Basically, you can use this definition to tell what the subtype relation means. That's the intent of this principle. And all the definition, which is a little bit easier to process, for each object O1 of type S, there is an object O2 of type T, such that all programs P defined in terms of T, the behavior of P is unchanged when O1 is substituted for O2, then S is a subtype of T. And for reasons that will be apparent in a moment, I'm going to stress on these all programs, right? So when we think about subtype relationship between two types, S and P, or S and T, or between base and derived, we should think about in the context of all programs, not just one particular subset of a program, but all programs, more than one program. Okay, so the Liskov substitution principle sounds good, but there are three problems with it, and I'm going to go into details. First, it doesn't work at all in a strict sense. Secondly, if we relax it, it's hard to use in this relaxed sense. And thirdly, we are hoping to reduce the complexity of our software by using inheritance. But what this principle tells us is that inheritance will actually increase the complexity in our software. So let's look at the strict sense. So we have a property phi of base, which is true. And it's provable to be true for all the objects of type base. And we want to see if that property is also true for derived. It better be true, otherwise Liskov substitution principle will tell us that this is not a good subtyping model. And let's define this property. Phi of x is true if and only if x equals base. That is, if derived is different than base, which it is in our case, then this property will be false. That means any type of base class and any type of derived class that we will have, if we think about this property, LSP doesn't make sense. It's completely broken. Let's look at the principle again. Subtype requirement. Let phi of x be a property provable about objects x of type T. It's provable. It's always true for our base class. Then phi of y should be true for objects y of type S, where S is a subtype of T. Well, that's false. It doesn't say anything that we should pick just a few properties is there. It's just for any property that's provable about objects of type T. That's the problem with LSP in a strict sense. And here is a simple code that will prove this. You can simply check for the type ID of the class, and if it's different than the base, it will fail. You can apply this to all of your derived classes, and it will fail. Mathematically, this proves that LSP does not allow subtyping. If we take LSP in a strict sense, let's try to relax a little bit LSP. Let's try to see where that got us. So behave exactly like base is a little bit too strict, a little bit too constrained. Let's try to find out what are the properties that we can think of. Return the same thing as base does. That is the same exact values. That means probably the behavior doesn't change. So calls exactly the same function as base does. Same functions, even additions, multiplications, and all the basic primitives, then it must behave the same. Same performance as base. Again, it's hard to make two different things, two different functions that perform two different tasks to have exactly the same performance. Return a subset of results that base returns. That's a little bit more relaxed. Has some invariance as same invariance as base. That's yet a little bit relaxed. The list can go on. Basically ad infinitum. I want you to think about when you did the last subtyping that you made, when you derived a class, how many of these properties have you thought of? And how many properties there are there which you haven't thought of? Probably there are a lot. So in a relaxed sense, the first problem that we see is it's hard to find a good property to apply LSP for. In order to find relevant properties for our code base, what we actually need to do is to survey all the code that we have to make sure that we haven't missed a property that we have somewhere in the code. So if some client of base depends on some property of that base, the derived class should better not invalidate that property. And how can we be sure of that? Well, we just have to survey all the code. And that's an extremely hard problem. Imagine a million lines of code base. Surveying all that code, it's a hard task. And let's look a little bit how things can break. So LSP can break for two main reasons. When changing the derived, if we don't know all the assumptions that we've made about base and the clients of base, and when changing the base class or the clients of base class, when we don't know all the assumptions for all the derived. Let's pick up two examples here to make this clear. So we have a button, we have some old client code that just pushes the button, and after it pushed the button, it asserts that the button is actually pushed, assuming that pushing the button cannot ever fail. But then somebody later on in a completely different module adds another button, a button with safety, in which the button cannot be pressed unless some other button is pressed. And you can find that in a lot of dangerous equipment that you have to have some kind of a safety. Well, that button with safety invalidates the properties that the client code assumes about the base, and this will actually break. The second example, let's imagine that we have an old derived class, a button with a timer, and then we add some client code. The button with a timer does something like you press the button, it's pressed, and then after 1 second, it just unpresses the button, so it automatically goes off. You can find those buttons in a lot of places in the real world, those types of buttons. And the client code does not know about this derived class. It just knows about the base class. And the base class, you see, it's push, and you can push it, and you can check to see whether it's pushed or not. And then the client code just pushes, checks that is pushed, it returns OK, waits a little bit, does some processing, and then assumes the button is still pushed. But this does not go well with our button with timer. So again, it breaks LSP. And I try to put on a very simple diagram the source of all the problems that we have with this. We have a base class and multiple derived classes, and the clients of that base class have indirect coupling with the derived classes. They do not only depend on the base classes, they also depend on all the potential derived classes that we can have here. And that's a big problem, because the client code and the derived class can be in different modules. And moreover, think about open-close principle. Theoretically, I can have an infinite amount of derived classes, and I can have an infinite amount of clients to my base class. I cannot know when I'm writing those two what the other party will do. And that actually increases complexity, because now when I'm writing derived, I not only need to know about base, I need to know how base is used, how all the properties that the clients of base will imply about my base class, in order for me not to break that behavior. So if we are looking from this perspective, inheritance is not an abstraction, because an abstraction should reduce complexity, and we just proven that it actually increases the complexity by a large margin. So to sum it up, LSP does not work in a strict sense for any problem. If we relax the sense in which LSP applies, then it's hard for it to work. And actually, LSP tells us that inheritance increases complexity, does not reduce it. So in this section, we talked about subtyping and why would we use inheritance for subtyping, and we proven basically that inheritance is not the best way to actually not is the only way, but subtyping is not quite okay when used this way. So let's move on. Inheritance and friendship. In real life, I want you to have this analogy in your head whenever you're comparing inheritance and friendship. Children should be more closer to you than your friends. Yes, you would tell your friends things that you would not tell your children. Your friends may have access to some information that your children may not have access. But in general, the children can affect your life far to a bigger extent than your friends. Okay, too much analogies, that's a metaphor that will break at some point. Let's see the impact of friendship. The friendship relationship may guarantee that your friends classes can access to your members, to all your members, and that's a bad thing. We know that we've all been told to avoid friendship. And if you are a little bit careful, the good side of friendship is that it doesn't necessarily change the interface of the class. You just have to look at the same invariants, the same properties that you have for base, and the friend class just have to do the same thing for it. On the other hand, inheritance has a different type of impact. It can access most of the members, so not all the members, but most of them. But it can change the class invariance, as we just seen. You can implement a behavior in the derived class that completely changes how base class reacts, and it's hard for you to notice that, because that depends on the polymorphic use that your clients will have. So that means that your inheritance will tend to affect all the clients that you have for your base class. There's not necessarily a direct relationship. It's an indirect one, but still it's potential to affect that thing. Let's look at an example here. So I do have some strange coupling. This is not necessarily unheard of. People do that all the time. We have a flying thing as a base class with a lot of logic inside it, and we have two instances of the flying thing, an airplane and a duck, because why not? They both fly, so we think reuse is good, so we reuse flying thing. And then we have a user for the airplanes and a user for the ducks, whatever that may be. The problem is that the airplane user is coupled with the duck user through this inheritance relation that we have. Imagine that the airplane user needs something specific for the airplane, a new change in the flying behavior, and that change is not necessarily explicit in the interface that we already have. So you have to change slightly that interface, and because you put a lot of your logic inside the base class, or because maybe the interface is just defined in the flying thing, even if your implementation is in airplane, you're going to touch the flying thing base class with that set of change. Again, this is not something that it happens all the time. It just tends to happen in a lot of cases, and I've seen too many examples for a lifetime in which this happens. But when you're trying to make these changes to the airplane user, which affects airplane, which affects the flying thing, you indirectly affect duck. The duck doesn't care about the flying behavior of an airplane, but it's still affected by those changes. And if duck is affected, then the duck users are affected. And therefore, you have an implicit coupling between airplane user and the duck user. And typically, in practice, this is associated with another thing, with some kind of a change inertia, in which instead of refactoring flying thing to really decouple the airplane and the duck, what you end up doing is add more logic. If you add more logic, you make your stuff even more complex. If you make your stuff more complex, then it's even harder for you to refactor it. And then the next time you have to do a change, you add more complexity to it. And soon you reach a point in which the complexity is so high for such a simple thing that it's really, really hard for you to change those things. So the conclusion that I have from this is that if you look at it from this perspective, inheritance is stronger than friendship, because it doesn't necessarily affect you in a short range. It doesn't just affect you the classes that are in that friendship relation. It affects you in a much deeper sense. It affects all the clients for that, and maybe all the clients of those clients, because as you see, this is a transient dependency. Okay, let's move on. Inheritance versus composition. I'll start again by quoting Bob Martin when he was talking about the rectangles and the square example. A pox on the either relationship has been misleading and damaging for decades. Inheritance is not either. Inheritance is the redeclaration of function and variables in a subscope. No more, no less. That is, if we think about what we said about inheritance, Bob Martin doesn't quite consider subtyping in his statement. It's just, he says, it's just redeclaration. So it adds even more confusion about what is this inheritance thing. Well, the proper way to do a redeclaration is to use composition, because you don't have to copy the same code over and over. You just abstract it out and put it into some common implementation. Of course, you have to do some small typing in each class, saying like, okay, this function now calls my behavior function, which is in a different class. But come on, it's just a couple of characters that you have to type. It's not such a big deal. And I'm going to quote again from Sutter and Alexandrescu for this. Inheritance is overused, even by experienced developers. A sound rule of software engineering is to minimize coupling. If a relationship can be expressed in more than one way, use the weakest relationship that's practical. And this is actually from the chapter named Prefer Composition to Inheritance. Composition is weaker than inheritance. So whenever you have the chains, try to use composition compared to inheritance. And since we are talking about composition, I think it's worth mentioning Klaus's talk from yesterday, Breaking Dependencies, Type Erasure Design Analysis. That's some form of composition that he was advocating there. I'm not necessarily trying to solve the polymorphism part of using interfaces, so that's why somehow I don't necessarily go into that direction. But I think his approach in there is a very, very good way in which you can solve a lot of problems that you may typically want to solve with inheritance with a much simpler approach. And the talk was so good that even my cat was fascinated about it. So yeah, good job, Klaus. So why do we use inheritance? In this chapter, we just talked about reuse members, and we show that it's not necessarily the best idea to use inheritance for reusing members. We have composition, which is better than that. So let's put up things together, and let's try to draw some conclusions when to use inheritance and when not to use inheritance. So at the beginning, we said that we would want to use inheritance, or people would want to use inheritance for these reasons: model real-world concept, reuse members, subtyping, and implement an interface. And basically, for the first three, we went over them from various different perspectives, and we've shown that inheritance is not necessarily the best thing that we can use there. And especially for the reuse members, you can use composition for that. Subtyping doesn't quite make sense. You find better ways to do that. But still, we haven't discussed about to implement an interface. And that's something that is not necessarily bad. It can be in some cases, but not always, and not in this generalized way. So we can still use inheritance with interfaces, and as much as possible try to replace by composition. Again, interfaces may not necessarily be the best solution. Sometimes it's the most convenient one, but there can be a good way in which you really want to use inheritance, you can use it. Okay, so let's go a little bit of interface and let's see how they would apply. So they work relatively okay with the Liskov substitution principle. You can still find things in which they break, but in general, it's much harder to break them because interfaces, by definition, are fully abstract. So the only thing that you're defining there is purely abstract, is an abstract thing. It's harder for you to put there things that would affect the derived and the clients together. But you can still have the same type of failures that we've seen before. It's just a little bit harder to do that. And actually, it works really well if we consider the other solid principles in there, especially interface segregation. So let's just pick one simple example. Let's have a duck, and we put a lot of things into duck because that's how that's how we seem to other people. It just tends to happen. The common excuse is, forgive me the pun, we inherited this from some other developer. And we do have some different types of duck. We have the mother duck, we have red hat duck, and we do have some artificial ducks like rubber duck and electronic toy duck. And they all implement different types of behaviors. The first thing we can do here is we can extract out the common things and use composition here. And the diagram would look something like this. It's not perfect. It still has some problem, but it's starting to be a little bit more more laid out. You extract the behavior and put it into some common parts. You still have some things in the base class swim, which doesn't make sense for a lot of the things. For a rubber duck, you still have the fly interface. You have some kind of a no fly behavior, which doesn't make sense. If you don't fly, you simply don't implement that. But it's a step forward. And if you just go over the next level, you can make all of those into just pure interfaces and use them like that. So you would have a pure interface that just have fly, have a pure quackable interface that just does the quack thing, have a displayable element that you can just display things. And then the whole hierarchy simplifies far more. Again, this is not the best solution. Don't think of it as is. I'm just trying to provide a few tips in how you can take a messy inheritance-based solution, just by some changes, try to simplify it a bit. And for the interfaces, I guess the guidelines would be the classical ones in Solid. You should have one interface for each type of client. And I think the more important part here is that the invariance of the interface should be directed by the client. If you can design your interface in such a way that you can capture in the essence of the interface how it's going to be used by clients, then basically you achieve this decoupling between clients and the implementations of your interface. There's not necessarily an easy thing to do, but I think in most cases people can manage to do that. In that sense, if we are going to achieve that, then we can decouple concrete classes from users. And when we do that, then basically we would have a proper abstraction. The interface is a proper abstraction for all the concrete implementations. So once again, when should we use inheritance? We basically went over all these reasons, and the only valid reason is to implement the interface. Again, not necessarily that you have to use inheritance, you have to implement interfaces. There are other ways. Think about the type erasure pattern that Klaus expressed, but that's when you would use inheritance. And for the other uses, doesn't quite work. Please don't use it like that. So in conclusion, inheritance is full of inconsistencies, full of confusions. It's overrated, and the sad reality that it's still overused in our C++ practice. Thank you very much. I'll be expecting questions. If you can put them into Q&A. Okay, so one from Klaus. Inheritance seems to be the only way to design for an open set of types. If inheritance does not work, could you name an alternative that we should use? I don't think inheritance is the only way to design an open set of types. I think the obvious alternative is the one that you proposed yesterday with type erasure. Yes, it has some inheritance inside, but it's private. And you can think of implementing the same thing without inheritance. It's just more complex, but you can think of it implementing in those terms. The thing that I was not focused in my presentation is on polymorphism. So most of the time you want inheritance to implement polymorphic behavior. And we somehow have this mental trigger whenever we think about polymorphism, we somehow always think of subtype polymorphisms. Subtype polymorphism is not the only way of polymorphism. You can think of parametric polymorphism, which C++ uses for templates. It's also polymorphism and does not need inheritance. And the functional languages make a great use of parametric polymorphism. C can have polymorphic behavior without using interfaces, without using inheritance. Sorry. So there are a lot of other ways in which you can implement polymorphism. And I think that's what you mean by open set of types. Hope that answers the question. Any other questions?
There seems to be one other question in the chat. Hani asks, by the way, if ISA terminology is a confusion here, will it be worse to think of a new name rather than with inheritance?
So I guess even harder than having confusing terminology for inheritance is naming. Naming is a hard problem in software engineering. So I'm definitely not good at naming things. So no, I cannot offer a better name for inheritance. And there are a lot of alternatives to inheritance. Even if we change the name of inheritance to, I don't know, member reuse or whatever, or subtype relation, the same problems would still appear.
Okay, I think there are some new questions in the Q&A tab now. So.
Okay. Should we try to teach the... Actually, I should read it, the other one first. How can we enforce in C++ that interfaces like flyable are really bad interfaces without you can somehow safely use multiple inheritance? So only pure virtual functions, no data member, etc. As far as I know, there is no real support for this in the language or STL. Or read more with dot. Or is it? Unfortunately, we do not have that support in the language. I'm curious to see whether the standard community will eventually move into that direction. Maybe if we have meta classes, then we can force that type of behavior. But I'm not up to date with the efforts on meta classes. But yes, I would somehow really want this this thing in the standard. And moreover, I would want our community to be more firm on using inheritance for everything is not such a good idea. hope that answers the question. So, Radek, should we try to teach the community to distinguish between implementation inheritance, resulting inheritance, and implementing interfaces resulting subtyping? It seems like these two different things are often interchanged when talking about inheritance. Yes, I think we should do that. Yes, there are times in which you would want to do, for simplicity reasons, you would want to do the traditional implementation inheritance. But in general, what you would want when you use inheritance is to use interface inheritance. So yes, we should try to teach the community. Klaus, to clarify, open set of types according to OCP, I can add new types without modifying existing code. So sorry. So if you add new types without modifying existing code, if you're, let's say you add new types in the derived part of the system, that means, let me try to go to that slide quickly. So if you add more classes to your system in the derived part, then in order not to break your code, is you have to make sure that the client is using some assumptions from the base that are not broken by your derived class. So essentially, the derived class that you're adding should know about the client code. And the same thing, if you're adding code on the client side, you should know about the direct classes that you have in your system. Does that make sense? If not, please add another question here. Okay, so Thomas, you quoted Robert C. Martin several times. That I miss is that solid also contains LSP. I agree that inheritance is not solving all problems, but it is one tool you have with language like C++. And there are others, but why rule it out completely? The big problem we have with software is, and that's an unfortunate reality, is we have more bad code than good code. And I don't want to just criticize the industry. If I look at my code, I have more bad code than good code. So just the fact that something is there and we have it in our inheritance doesn't mean that it's good. We have a lot of code that uses inheritance. We have a lot of code in which we try to apply Liskov substitution principle, but it doesn't mean necessarily that that inheritance is good, or whenever we applied LSP, we applied it correctly. Don't get me wrong, there are a lot of cases in which we apply LSP correctly. What I'm trying to prove is that applying it correctly, it's extremely hard, because if you're a good engineer, then whenever you're doing a change, you have to know the complete impact of your change. And in order to do that, with inheritance, you basically have to know the rest of the code. You can't simply rely on some abstraction that your base class has. That's the big problem there. I hope that that answers the question.
Okay, thank you again for the great talk and interesting discussion. If there are any further questions, I assume you will be available at the table for further discussion?
Yes, I'll be in table.
Wait, there has come up one more question. Is the Liskov substitution principle compatible with protected members from base?
So I hope you're not referring here about protected inheritance. That's a completely different topic, which is somehow a mix between the danger of public inheritance and the safety of it. So I'm trying to refer to LSP related to the fact that you have access to protected members. The problem with LSP is not about how much access do you have to your base class. Is the problem to how much can you change from the base class. If you're allowed to change something from the base class, then basically you can break all the client code. That's the problem with inheritance. And that's the problem where LSP is not strong enough to give us a clear guidance on how to do it. I hope that answers the question. Here's another one regarding favoring composition over inheritance in places where inheritance is to be used. I believe composition has a relationship. Then how the terminology match here? So instead of making a plane inheriting from a flyable thing, we should say plane behaves like a flyable. Well, we can say from start behaves like a flyable thing. That means that plane has a behavior of that type of things. We can do that by an interface, and the actual implementation of the flyable thing we can delegate to somebody else. We can delegate to some flying engine, for example, which can be used by a plane or a helicopter or whatever, if that is generic enough, and if that matches the problem. Therefore, we are not associating plane with engine behavior in an either relation or behaves like relation. We associate it with has a relation. So plane has a, I forgot the name I just said, engine, flyable engine. I think that that clarifies. So whenever we are changing inheritance for composition, we should change our terminology. We are changing the names of the classes anyway. Seeing the chat, Klaus says, is it hard? That should be the real summary. Yes, that is the real summary. It's hard. It's really hard to use inheritance correctly, and it gives us a lot of pain. Okay, it's hard for me to skim the chat for questions. So I'll be going then to the chat room, and if there are more questions, you can find me there. Thank you very much, everybody. See you there. Have a nice day. Bye.